All right, so today's topic is an introduction to solving non-linear systems. We've already looked at linear systems where we're looking at the intersection of two lines. So now when we're saying non-linear, that simply means that at least one equation is non-linear, so not a line. So the possibilities that we look at first are lines and parabolas. And then a second possibility is two parabolas. So if we're looking at a line and a parabola that have no solution, right, that means that they're just never going to cross. So I could have a parabola like this and a line that looks like this, for example. There are 0 points of intersection. If I'm looking at two parabolas, maybe I'm giving you two parabolas that open in opposite directions like so. Either way, no solution. If we're looking at one solution, here could be my parabola, and then here could be my line that's making contact right there at the vertex. Or maybe I have two parabolas that touch at the same vertex, but one opens up and one opens down. Okay, another possibility is two solutions, 2 points of intersection. So I could have my parabola like this, my line like this, 2 points of intersection. And if I'm looking at two parabolas, I could have one that looks like this, one like this, and again, 2 points of intersection. Okay, the first way that we have you solve nonlinear systems is a graphical approach, a visual approach, and then we're going to segue into doing it algebraically very soon. So first, graphically. So my first equation right here is a parabola. I recognize that it's in standard form. So to get to my vertex, I'm going to use x equals negative b over 2a. That's going to get me the x coordinate. So a negative 1 times a negative 2 over 2 times 1. So 2 over 2 is 1. The x coordinate of my vertex is 1. Plug it in to get the y value. So y equals 1 squared minus 2 times 1 minus 8. 1 minus 2 minus 8. 1 minus 2 is negative 1. Minus 8 is negative 9. So my vertex is at 1, negative 9. Plot it on your graph right here. Now, since the a value is just 1, I'm going to plot it with just my parent function points. So over 1, up 1, back to the vertex. Over 2 and up 4. Back to the vertex. Over 3 and up 9. Those are actually the x-intercepts. If I had factored this, I could have seen those x-intercepts a lot faster. Okay, I have more room on my grid, so over 4, and 4 squared is 16, so up 16. So here I'm up 9, 10, 11, 12, 13, 14, 15, 16. Puts me right here. Let me match it on the other side right there. All right, so now I'm going to connect my dots and make my parabola. Okay, second equation is a line. I recognize it as y equals mx plus b. My m, my slope is 2, and my y-intercept is at 0, negative 3. Plot a point at the y-intercept and build off of it the slope. So up to right 1, giving myself a lot of points, and then going in the opposite direction as well. Okay, so here is my line. And then my two solutions, my 2 points of intersection, are here and here. So here I'm at -1, -5. And my second one is right here at 5, 7. If I wanted to double check, I could always plug these coordinates and these coordinates back in and confirm that I get a true statement. Okay, next set of 2. We slide it up. All right, so 2 equations. That first equation, I can recognize it as a quadratic function, so it graphs as a parabola. And so is the second one, right? Because I recognize that I have a quantity squared. So here again, I can get my vertex really fast. It's in vertex form. 1 right, 5 down. So 1, -5. There's my vertex. So right there. Okay, I can see that the A value is just 1. So I'm going to graph it using my parent function points. So over 1, up 1, back to the vertex, over 2 and up 4, back to the vertex, over 3 and up 9, here and here. Connect the dots. There is your parabola. Okay, second one here, also a parabola. I recognize the quantity squared. Okay, 2 right, but it's not moving up or down. So my vertex is just at 2, 0. Right here. Okay, from there I can see that there is a vertical flip, right? Because I see the -1 right here. So over 1 and down 1, back to the vertex. Over 2 and down 4. I see the points of intersection already, but I'll just give a few more points. Over 3 and down 9. And then connect the dots. Okay, so here again I have 2 points of intersection. So right here at 0, -4. And then right here at 3, -1. All right, last one. All right, that first equation I recognize as a circle, and we haven't seen circles since geometry. So here it's a circle. My format here is x squared plus y squared equals the radius squared. So since this is my radius squared, that simply means that my radius has to be 5. Right? Technically, I would solve, I get plus or minus 5, but my radius is a distance. It must be 5. Okay, and then I'm centered at the origin. Okay, just to remind you about a circle, let me bring this in for a moment. So just watch this for a moment. So here I'm centered at the origin. The way that I get that equation for a circle is really through the Pythagorean theorem. Let's say that I put a point right here and I connect it back to the center. I can make a right triangle out of it like so, where this is the horizontal distance, the vertical distance, and then the radius. So I can see that it's really just the Pythagorean theorem. X squared plus y squared equals the radius squared. Okay, but I can have another point over here. And if I connect it back to the center, that's still the radius. But I can see that I have a different x and y value that are joining together to still produce the same radius. I could put a point here, make a radius, visualize the right triangle with a different x and y coordinate that gets me to this point right here with this radius right there. So really all that circle equation is the Pythagorean theorem. A squared plus b squared equals c squared, where x and y are points on the circle where the radius is staying constant at 5. Right? That's what it is in my example here. All right, so then let's say that we start with the circle. I'm starting at the center, the origin. I'm going to go up 5, left 5, down 5, and right 5. But I can actually get more points because I remember that my most common triple is a 3, 4, 5. So common sides to a right triangle. So now imagine that from this center, I go over 3 and up 4. I go left 3 and up 4. I go left 3 and down 4. I go right 3 and down 4. It's going to give me more points on my circle. What if I looked at that same right triangle, but I reversed where I put the legs? My hypotenuse is still 5. I can add more detail by going right 4 and up 3, left 4 and up 3, left 4 and down 3, right 4 and down 3. So all I'm getting is more points on my circle. These are all of the points that will have integer values for x and y. All right, there's my circle. Okay, the second one here is a parabola. I notice because I have an x to the second power, so a parabola. Okay, I can see that it's 6 left, 1 up. So my vertex is -6, +1, and it has a vertical flip to it. So left 6, up 1. Okay, and then from here, I'm just doing the vertical flip. I'm opening down. So over 1, down 1, back to the vertex, over 2, down 4, back to the vertex, over 3, and down 9. So here and here. So my 2 points of intersection here will be at -5, 0. And at -4, -3. Okay, and just to point out other intersections you could have with circles. Let's say that I'm looking at a circle with a line. I could have no intersections. I could have 1 intersection. I could have 2 intersections. Let's say that I'm looking at a circle and a parabola. Let me give myself a couple of circles to build off of. I could, of course, have no intersections. I could make contact in 1 spot right there. Right? I could have 1 point of intersection. I could have 2 intersections. I could have 3 intersections. Like that. Or I could even have 4 intersections like that. So lots of possibilities with intersections with circles, right? Whether it's a line or with a parabola. All right, have a good rest of your day.